Hello viewers, welcome to this part of the course. Today we are going to continue our discussion on FM demodulator circuits, and we will today talk about two detectors, which is balanced slope detector and PLL based detector. Then after that we will talk about comparison of amplitude modulated, frequency modulated and phase modulated signals, whereby we will talk about how the performance of AM, FM, PM is different for different kind of nonlinear distortions that we can encounter in a communication circuit and communication channel, and how this behavior is also different in terms of frequency occupancy, amplitude variations, and against the kind of noise which we encounter into the communication transmission. Continue our discussion on FM detection, and last time when we talked about slope detector, we discussed that the biggest drawback of a slope detector is that it has linear response only over a very narrow band of frequencies, whereby it is not very useful for wide band frequency signals. So now what we are going to do is that we are going to look at a improved version of slope detector, which is known as balanced slope detector, and we will learn about its functioning and see how it can improve the performance in terms of the larger frequency range over which the frequency response of the detector is linear. So in balanced frequency discriminator, what we do is that we use two resonant circuits, and these are tuned in such a way that one of the resonant circuit is tuned to frequency which is above carrier frequency, and another frequency circuit, resonant circuit, is tuned to a frequency same which is having same separation from the carrier frequency, but it is at the lower side of the carrier frequency, and then get a differential output at the output, and whereby we can actually get response of filter and the detector which is linear over a much wider frequency range than it was for a individual resonator circuit. So in the next slide what we see is the balanced frequency discriminator circuit. We have a transformer which is fed with the received signal, frequency modulated signal, and we have a secondary coil which is where the upper coil is tuned to a frequency F01, which is higher frequency than Fc, and lower coil is tuned to another frequency which is F02, and it is lower than carrier frequency. And then we have two differentiate envelope detector circuits which are being used. There is a diode, there is a RC circuit, and then we get output from V0. So for this kind of balanced slope detector, if we look at what is the frequency response, so in the next slide what we have shown is we have shown the amplitude response for the tuned filters for upper resonator circuit and lower resonator circuit. Upper resonator circuit response is shown by a blue line, and lower resonator circuit response is shown by a green line, and the cumulative joint amplitude response is shown with the red line. We can clearly see that the response of balanced slope detector or the two circuits together is linear over a range of 3B, which is much higher as compared to any individual tuned circuit, whereby we can overcome the biggest limitation of slope detector, which has a narrow band response, linear response. The overall performance of balanced slope detector depends on several parameters. One of that is both the filters should have high Q factor, and there has to be a proper frequency separation between the tuning frequencies of the two filters. However, even in the case of balanced slope detector, we have few distortions which are still there. One of that is that since the FM spectrum is not having zero amplitude outside the frequencies, so we have some kind of distortions which are coming due to the aliasing kind of effect. Then the tuned filters are also not having strictly band limited response. So again the symmetry what we assumed for the getting the linearity in the balanced slope detector performance will not be there if there is a mismatch. And then the RC filters in the envelope detector introduce distortion, which are the same distortions which we talked about in envelope detectors for amplitude signal. One of the loss is diagonal loss, where RC constant is slower than the modulating signal variations, or the loss which is due to the when the RC constant is not properly chosen and it starts following carrier variations. Also, tuned filter characteristics are not linear over the whole frequency band here. So, again this is a limitation. It is better than the slope detector, but again this is having a limited range over which the frequency response is linear. Now, we move to the second kind of demodulators or type of demodulators, which are called tuned frequency circuit demodulators, and the example of that is PLL. PLL circuit can be used to track the frequency variations in the input signal, whereby produce output voltage which will be varying proportional to the modulating signal. This approach is especially useful when you have low SNR conditions. The same method using PLL can also be used for demodulation of AM signals, and what we have is that in a PLL we get a VCO which is in the feedback loop, and this VCO is used to track the input fluctuations or variations in the signal frequencies. This will be, once with these signals are tracked, the output voltage corresponding to the loop filter is going to give us the variations which are due to the modulating signal, and from there we can extract the information about modulating signal. In the next slide, what we see is a block schematic of PLL model. So, we have an input signal A cos omega ct plus theta it, where theta it is the input signal phase and omega c is the frequency of input signal, and this signal is fed to a phase detector or a mixer, which also gets second input from a voltage control oscillator, which is producing B sin omega ct plus theta naught t. So, in this particular case we have assumed that the incoming signal and the VCO output both are operating at the same frequency, and the variation or the difference is only in terms of the phase information, whereas in the real case we can also have slight variation in the frequency, which can, for without loss of any generality, can always be accounted as a phase difference. So, now if the phase difference between the incoming signal and the VCO output is small, then the phase detector output would be corresponding to theta I t minus theta o t. If this output is basically corresponding to sine component of theta I t minus theta naught t, but we have used here the fact that when x is very small, sine x value is equal to x. So, this phase error is then fed to a loop filter, and the output of the loop filter VO is fed back to the VCO, whereby this error voltage VO allows VCO to track the phase of input signal, and by now processing VO we can get the information corresponding to the modulating signal. So, the output of your VCO is let us say if the frequency of our VCO output is FC, then it is going to be k times VOT, where VOT is the output of loop filter and k is VCO gain. Then phase of VCO is going to be 2 pi 0 to t integral k V0 t dt, and from here we can solve for V0 t, which is going to be 1 over 2 pi k d theta 0 t by dt. So, we will make use of this fact that the error voltage output of loop filter is related to VCO output theta naught t. So, now we say that when loop is logged, the output phase of VCO is going to resemble closely with the phase of input signal, which is theta I t. So, if we make this substitution in the equation, we get V0 t is equal to 1 over 2 pi k theta d theta I t over dt. So, d theta I, we know how it is related for a FM signal to the modulating signal. We recall from our earlier lectures that for a frequency modulated waveform, theta I t is nothing but kf times, where kf is the frequency sensitivity of the frequency modulator, times integral 0 to t m tau d tau. So, now when we write our V0 t in terms of this expression for theta I t, we will get V0 t is equal to kf divided by 2 pi k times empty, where empty is the modulating signal. So, what we can see here is that output signal at the loop filter output is going to be proportional to the modulating signal. So, we can extract the modulating signal information from the output voltage of loop filter. This is what the method we can use for demodulation. This kind of method is performance of PLL based method is similar to the slope or balanced slope detector for the scenarios where the noise is not very high. So, small noise means PLL and frequency detectors using slope detector are going to have similar kind of performance. PLL gives much improved performance when the noise power increases. So, it has advantage in lower signal to noise ratio conditions. Now, since we have talked about the three modulation schemes, namely amplitude modulation, phase modulation and frequency modulation, we are going to talk about a comparative statement of these three modulation scheme, and whereby we will also talk about when to use which kind of modulation scheme. At the same time, we also must realize that the amplitude modulated signals were invented much before angle modulated signals. So, most of the initial systems which were operating using amplitude modulated signals were there because they were the only signals or modulation techniques known in 1920s. The signals corresponding to FM and PM and circuitries were invented much later, but still if we see today, there are commercial services which are both using amplitude modulated signals as well as FM or PM modulated signal, typically FM. So, here in this particular slide we see a carrier signal and a message signal which is a ramp signal. So, now if we want to understand by looking at a modulated waveform, can we identify or differentiate between amplitude, phase or frequency modulated waveforms? So, for that what we should do is we should take a message signal which is kind of ramp. So, in the amplitude modulated waveform we will see that the amplitude of the modulated signal will be changing linearly with the amplitude of the message signal which is ramp. In the phase modulated waveform, what we will see is that amplitude is constant, because in the case of angle modulated waveform which is both FM and PM, amplitude does not change. The change and the variation in phase modulation is not even there in terms of the frequency, because frequency is maintained constant, because the ramp signal will be incrementing at a constant rate. So, the frequency is also maintained constant, whereas in the case of frequency modulated signal we can see that the frequency is continuously increasing with the magnitude of the modulating signal. So, where if we take a message signal of this type, we can easily identify by looking at modulated waveform whether the modulated signal is AM, PM or FM. Now, we go into the more important details, which are mainly how these signals perform when you encounter some nonlinear distortions. Typically, in any transmitter system, the last subsystem is power amplifier, which are nonlinear devices. So, it is very important to understand how various modulation schemes perform when the signal passes through this nonlinear amplifier. So, we first look at the performance of PM and FM signals at the output of any nonlinear device. So, we consider nonlinearity which is of this nature, that yt is equal to A0 plus A1 xt plus A2 x square t and so on, where xt is the input and yt is the output. Now, if we consider our input to be an angle modulated signal, then we can say that xt is equal to A cos omega ct plus psi t, where psi t is the phase which is due to the modulating signal, and it can be for both AM, FM or PM, and the corresponding output of this nonlinear device is going to be C0 plus C1 cos omega ct plus psi t plus C2 cos 2 omega ct plus 2 psi t plus so on. What we see here is that this nonlinearity will produce harmonics of the signal, input signal. Now, what we can do is that if we can use a band pass filter, we can extract one of these harmonics and we can get rid of all the amplitude or distortions which were introduced due to the nonlinearity. What it means is that FM and PM signals are immune to the signal nonlinearities. If we can use a band pass filter at the output of nonlinear device, we can completely eliminate the distortions caused by the nonlinear device. Whereas, if we now consider an amplitude modulated signal to go through these nonlinearities, so we consider a nonlinearity which is of third order. So, y t is equal to a x t plus b x cube t. We could have considered similar expressions, but that would have been very complex to explain the phenomena of the kind of distortion AM signals go through. So, we are just taking a simple nonlinear equation of third order, and now if we take that the input signal is DSB SC modulated signal, which is given by mt times cos omega c t, the output of the nonlinear system is going to be y t is equal to a mt cos omega c t plus b m cube t into cos cube of omega c t. Now, what we see here is that the first component is corresponding to the linear term and the second component is corresponding to the third order nonlinearity into the system. Now, when we solve using some trigonometric identities, we can write this expression as a m t plus 3 b by 4 m cube t times cos omega c t plus b by 4 m t to the cube times cos omega 3 omega c t. What we see here is that even if we want to extract the information signal corresponding to m t, we will get a signal distortion also. So, what we see here is that if similar kind of band pass filter is used here, we will get at the output of band pass filter a m t plus 3 b by 4 m cube of t times cos omega c t, and we can see that the envelope of this signal has a distortion because there is a m cube of t term which is there with the desired term m t. So, what we see here is that amplitude signal, when they passes through nonlinearity, they have distortion, whereas when FM or PM signals are passed through nonlinearity, by use of a band pass filter we can get rid of all the distortions which are introduced. Now, we will talk about the effect of interference on FM or PM signal. So, what we do is that we, to understand this process, we take a unmodulated carrier and interfering sinusoidal signal which is of amplitude I and is having a frequency offset from the carrier denoted by omega. So, the received signal what we are going to consider is of this type, that A cos omega c t, which is the unmodulated carrier, plus I cos omega c plus omega t. So, where I is the amplitude of your interfering signal and omega is the frequency offset for the interfering signal. Now, we know that for detecting this FM or PM signal, we need to pass it through a differentiator and then envelope detector. So, what we look at is that when we pass this signal through a demodulator, what is the output we will get. So, in the output we will get a term corresponding to interference, which will be of the type I over A sin omega t, this is for phase modulation, and I omega over A cos omega t for frequency modulation. What we see here is that the interference component which appears in the differentiator output is inversely proportional to A. So, whereby what we can do is that if we decide very high amplitude for the carrier, we can suppress the interference. So, what it means is that the smaller interference can be completely suppressed by the angle modulated waveforms. Now, we are showing a schematic of how these two FM and PM signals has a varying effect of interference. What we see here in the next plot is that for FM signal, the effect of interference keeps on increasing linearly with the frequency offset, whereas for phase modulation the effect of interference is constant irrespective of what is the frequency separation between the carrier and the interfering signal. Now, this effect gives us some insights. So, now if we want to understand which system is better or provides better immunity against interference. So, we can conclude from this expression that at lower frequencies the effect of interference on FM is much smaller as compared to phase modulation, but at higher frequencies the effect is more on FM as compared to phase modulation. So, can we do something? Can we have best of both worlds? What it means is that can we have a signal which is modulated like FM signal at lower frequencies and as PM at higher frequencies, because this will allow us to achieve best of the worlds. So, this can be done by using the two circuits which we call as pre-emphasis circuit and de-emphasis circuit. Pre-emphasis circuit is used at the transmitter and de-emphasis circuit is used at receiver. In pre-emphasis circuit, what we do is that we amplify the higher frequency components of the signal prior to transmission, and then the interference and noise effects will be added onto the signal, and then at the receiver side what we do is that we start attenuating the higher frequency component. The attenuation factor is similar to the amplification which was done at the transmitter side. The overall effect is that at the higher frequencies where the attenuation or if interference is high, when the signal at the receiver is attenuated, interference value comes down, whereas the signal value comes back to the normal what was the signal value before pre-emphasis. The resulting interference effect for FM broadcasting with pre-emphasis and de-emphasis is shown in this schematic here, where we see that with the pre-emphasis and de-emphasis FM broadcasting can achieve interference effect which is at lower frequencies follows FM variation and at higher frequencies follows phase modulated variation. Now, coming back to the amplitude modulation. So, the similar kind of interference if we consider for amplitude modulated waveform, what we see here is that then the received signal would be A plus mt cos omega c t, which is the amplitude modulated signal, plus I cos omega c plus omega t, which is the unmodulated sinusoidal interference having amplitude I and carrier of frequency offset of omega. Now, in AM signal what we are interested in is that the what is the envelope of the signal, because for demodulation of amplitude modulated signal we use amplitude envelope detectors. So, the envelope of this signal is going to be A plus mt plus I cos omega t square plus I square sin square omega c t. What if we solve, if the interference power is much smaller than A, then this value is going to be A plus mt plus I cos omega c t. So, what we see is that the interference is directly added into the modulating signal in the envelope, and the effective the effect of interference is independent of the amplitude of the carrier wave. So, we cannot suppress the weak interference, which was the case in the case of FM and PM. So, what we can conclude now is that FM and PM both signals are having immunity to nonlinearities as well as the interference. So, provide much improved performance than AM. The advantage of AM is its simplicity, because it requires only envelope detector circuit. Now, talking about the bandwidth versus noise trade-off. The bandwidth requirement for FM and PM signals are much higher as compared to AM signals, but also the effect of noise is much lower. So, the bandwidth the higher bandwidth gives you a better immunity against noise. So, there is a trade off between bandwidth and noise performance. The higher the bandwidth of FM signal, the better protected it will be against the noise. So, in this lecture we talked about balanced slope detector and PLL based detector, and we saw that in the lower SNR conditions PLL circuits perform much better as compared to balanced slope detectors. Then we also looked at what are the different other applications of PLL, that it can also be used for synchronous detection of amplitude modulated signals. Then we talked about the comparison of amplitude modulated signals with frequency and phase modulated signals, and realized that frequency and phase modulated signals are immune to nonlinear distortions, and also they provide much better protection against interference, whereas in the case of amplitude modulated signal we require a very simple circuit and much lower bandwidth as compared to FM and PM signal. So, in reality the choice between AM or FM and PM is basically based on the simplicity or the hardware complexity what we can afford versus what is the kind of bandwidth we can afford to have. In general, the quality of signal reception is good for FM and PM modulated signal as compared to AM signals. Hope you enjoyed this lecture. Thank you.